Hello everyone. So we'll be discussing today weekly contest 395. This is going to be the post contest discussion for all the four problems for today. All right. Let us start with the problems. First problem, find the integer added to array 1. All right. So you are given two arrays of equal length, nums1 and nums2, and each element in nums1 has been increased or decreased in case of negative by an integer represented by the variable x. So as a result, nums1 has become equal to nums2, and two arrays are considered equal when they contain the same integers with the same frequency. So this is like a very basic statement given to you, and you have to return that integer x. All right. So now if I read the problem, like if I see the constraints are also very small, and there's a very small note given to us that the test cases are generated in such a way that there is an integer x that nums1 will always become equal to nums2 by adding x to each element of nums1. So like it's must, like according to them, it's always there that you will definitely find an x for which nums1 does become equal to nums2 by adding or decreasing that number x in all the elements of nums1. All right. So now the intuition in my head actually runs towards the point that since the array needs to be equal, let's try to represent this thing. Like let's say I have been given the nums1 array. I have three numbers. I have a1, a2, a3, and then I want to create b1, b2, b3. So first of all, let's say I have some optimum x which I have chosen. So now my new numbers actually look like a1. Let's say I add on to this. Let's assume this is a1. This becomes a1. For a2, let's say I take the number as, let's say, a2 plus x, and let's say I take this as a3 plus x. Yes. So I know that they are getting increased only. Yes. Or like it's written or decreased in case of negative. That means like if let's say x was some variable that is in a negative order, let's say x is negative, then you will say this gets decreased. So either way, all the elements are either getting increased or they are getting decreased. In that case, we know that if I talk about the relative change in order, like let's say a1, a2, a3, since everything is getting increased by x, so I know that in a relative order, let's say previously, if let's say a1 was less than equal to a2 was less than equal to a3, then even after adding x, I know a1 plus x will be less than equal to a2 plus x will be less than equal to a3 plus x. Yes, because all these three elements still relatively order remains same. So now if that is the case, if I know that is the case, that means adding on x, if it's not changing my relative order, what can I do initially is I can sort the array A and I can sort the array B. Now once I've sorted the array A and I've sorted the array B, since I know their relative order does not change, and I know that the test cases are formed in such a way such that there is always an x for which adding on every x to every element in A becomes the array B. I know that if I sort both of them, then relatively they will be fixed in such a manner such that now if I add x to a1, a2 and a3 simultaneously, it will definitely be equal to b1, b2 and b3. Yes. Can we understand this with an example? Let's say I talk about the case number 1. So case number 1, the array is 2, 6 and 4, and the B array was 9, 7 and 5. Now if you sort both of them out, you receive an array. This is 2, 4, 6, and the array over here after sorting is 5, 7 and 9. Now can we see both of the arrays are equal only if you add 3 to every element. Yes, if I add 3 to 2, it becomes 5, 3 to 4, it becomes 7, and 3 to 6, it becomes 9. So that means when I sorted A and I sorted B, their relative order became same. And because it is must that an answer always exists, that is, there always exists a number x for which these arrays will become equal when I add x to every number in the initial array A, that means after sorting, both of the arrays will look kind of in this order such that their differences, that is 5 minus 2 is equal to 3, it's same, 7 minus 4 is equals to 3, it's same, 9 minus 6 equals to 3, it's same. The difference of bi minus ai will be equal throughout. Yes, can we extend this to the other cases? Let's say I talk about this case. So this case is, I think, like pretty simple case, so we don't need to think beyond. Like for 10 and 5, you know that the answer you will receive is 5, and over here also you can see the answer is 0. So they haven't given up pretty much they haven't given a lot of test cases for this theory to check out, but logically we can understand this, that since the relative order is not changing in the array A, because I am adding the same element to every element in the array A, that means after sorting array A and after sorting array B, their orders will match, and I can map 1 to 1 value, considering that an answer always exists. And that would make sense, because for the answer to exist after sorting, they will have equal differences, and that difference will definitely be the x value I am trying to find. So I think this is clear. Yes. So now if I've understood that this is something I can do, what do you think my implementation can be? As I just pictured, right? Very basic implementation. Just sort both of them. So like I'll say sort A, then I'll say sort B, and then I'll simply say return, because I know answer always exists, so I can say return B of 0 minus A of 0. Yes, if I do this, I will be getting the value of x, because after sorting B and after sorting A, I know that they have somehow fixed their relative order. They are now in a orderly fashion. Let's say I talked about those 3 elements, and there is only the missing number x that has not been added to every element in A for it to become every element corresponding to B. So I can simply say that since the answer always exists, differences will be equal. So even if I print any one difference, like I can even print B of 1 minus A of 1 if that element exists, but to be like very safe, I can say that since array can have a single element also, so I can simply print B of 0 minus A of 0, and that is going to be my correct answer. Alright, so now if I actually look at the code part, this is going to be very simple to understand. Right? Let me expand the code. Sort nums1 and nums1 totally from begin to end, sort nums2 from begin to end, and then simply print nums2 of 0 minus nums1 of 0. Alright, so now if I talk about the time complexity, so we are using an STL function of sort, and this runs in n log n complexity. So I will have let's say nums1 order is like let's say n, and like nums2 order, let's say this size is n, and let's say this size is m. So I can say time complexity is going to look like somewhere like n log n plus m log m. Now whichever is the superseding term, we can take that component to be the main time complexity. And now what about space? Am I using any added data structure to store the space? No. So I can say space is also in order of, it's constant, it's in order of 1. Alright, so now for the given constraints in 100 value, you know n log n plus m log n solution will definitely work, and that is why it is getting accepted. Yes, if I submit this out, we can actually easily see that this is getting accepted. Yes, gives us a correct code. Alright, so I think now we can move on to the second problem. First problem is easy enough to understand due to this relative order. So once this hits you, the problem is very easy to implement, right? I have just written literally 2 lines of code to actually implement this out. Alright, now the second problem. Now the second problem is obviously an extension to the first problem, because you can read that we are having find the integer added to the array 2. So this is part 2 basically of the first problem. Now how is it different? There is only a single difference with the first and second problem. It's written that you will be given the 2 integer arrays nums1 and nums2, and from the difference is that from nums1 2 elements will be removed, right? 2 elements will be removed, and all the other elements now will be either increased or decreased in the case of negative by an integer represented by the variable x. So you will choose an integer x and you will add that x to every element. From that, either elements will automatically get increased, or if x you choose is negative, so they will get decreased. Either way, whatever happens. But you are going to do this after you remove exactly 2 elements. And then it is clearly written as a result, nums1 will become equal to nums2. 2 arrays will be considered equal so that they contain same integers with same frequencies. Return the minimum possible integer x. So now the question is pretty much changed. Now they are not saying initially that nums1 and nums2 have the same equal length. Now they are saying very clearly, like it's given in the constraints also, that nums2 size is actually lower than nums1 size by 2. So nums1 size is 2 more. And that 2 more is actually the 2 extra added elements which you have to remove. After you remove 2 elements from array 1, you will try to figure out the same ideology as we did previously, and actually report to me the answer which you think is suitable. So I'll say that, let's say nums1 is given to me. So I'll modify the question. I'll say nums1 initially is not A1, like it's A1, A2, A3, A4 and A5. Let's say there are 5 elements. And nums2 is A1, A2 and A3 only. So there are 3 elements over here only. So I'll call this as B1, B2, B3. That's better, right? Now, what will I say? I'll say that I will first choose to remove any 2 elements. So I'll say maybe I'll remove A2 and I'll remove A4. After I do this, my modified array will be A1, A3 and A5. And now in this array, this array should be equal to this, the B1, B2, B3 array, if I add some x to this. So if I add a common x to all these numbers, that is some x over here, some x over here, some x over here, then they should have the equality. Or indirectly you can say that the differences, corresponding differences of, let's say, B1 minus A1, B2 minus A3 and B3 minus A5, these differences should be same. If these differences turn out to be same, let's say that difference is called diff, then I know that that difference is something I need to store, and out of all such possible combinations of removing any 2 elements from the array 1, I would require these all possible differences which exist, if they exist, and out of all such differences, I want the minimum difference. So this is pretty much the question. Yes. So like if I look at the array over here, they have clearly said that, let's say in this array, you remove the first and the last element. So after removing that, what happens? The array over here that after you remove the first and last element is actually 20. Like if you take over here, this is 20, 16, and then I have an array 12. Yes. And then over here, I have the array 14, 18, and 10. Am I correct? Yes. Now, what will happen? Same ideology by our previous question. If I feel that they are actually going to fulfill my difference condition, that means after sorting the array 1 and the array 2, their differences should be same. So I'll sort the array 1, it will become 12, 16 and 20. I'll sort this array, it becomes 14, 18, sorry, not 14, starts with 10. So this becomes 10, 14 and 18. Now if I find the differences, that is nums2 minus nums1. So this is negative 2, this is negative 2, this is negative 2. Yes, 10 minus 12, 14 minus 16, 18 minus 20. Are these 3 differences same? Yes. That means this difference for x is a valid possible difference when I would have removed these 2 elements. And I need to minimize such differences. So negative 2 obviously gets stored as initial answer, you can say. And then out of all such possible combinations, I'll further try to reduce negative 2 if I find more potential answers. Alright, so I think the question is pretty simple now. The question is pretty well clear and it's just an extension of problem 1. Now, how do you exactly remove 2 elements? Like you want to remove exactly 2 elements, but there are all possible combinations to remove these 2 elements. This is where constraints play into picture. Now this becomes a mental note for you, right? If I look at the constraints are only 200. That means both arrays are going to be in order of 10 raised to 2, or to be very specific, 2 into 10 raised to 2. So do you think I can run a brute approach now? What do I mean by brute approach? When I say brute approach, what will I say? I can run 2 for loops with an I pointer to n, inside which an inner for loop with a j pointer also to n. And every time I have 2 indexes I and j, such that I know I is not equal to j, I can actually say that I will, inside this inner for loop also, create the new array which can be called as the updated nums1, in which I would have skipped the element kept at the index I and the element kept at the index j. Once I do this, I will receive an updated nums1 array. Now this updated nums1 array, when compared to the nums2 array, in the similar process of how we did question number 1, if gives me a difference which is a potential answer, I can minimize that. And now I know, since I am using 2 for loops and I am iterating in such a possible manner such that I am able to receive all I and j pairs, I know that this is going to be a correct answer. But the problem to think is, will this work? And the answer to this question will be yes. Why? Because if I actually calculate the time complexity for such a solution, I will see that I will have, let's say this will run in order of O of n, and this inner loop is also going to run in order of O of n. Yes, that means up till here I will have a n square solution. That is definite. And now inside this, to actually create the updated nums1 array, I will again have to iterate, let's say with a k pointer in the total length n in the nums1 array. So this will be iterating in the nums1 array so that I'm able to skip the indexes I and j. Yes, and to skip the indexes I and j, that would mean very clearly that what I can do to create this, like for this added time complexity, O of n will get increased. So this actually becomes now n cube. Now, even if this becomes n cube, this is the highest possible time complexity I'm achieving right now, n cube is going to work. Why? Because n is in order of 2 into 10 to the power 2. So n cube will be in order of 8 into 10 to the power 6, which is much lower than 10 to the power 8. That is the number of operations, elementary operations you can do in 1 second. That means I know, like this is lower. I know that such a solution is going to work. It is not going to give me a TLE. Yes. So again, I'll repeat the approach. What will we do? We will do the same calculation we will do after creating the updated nums1 array, such that we did this in question 1. So after this, everything will be about question 1. That is common. But before that, we will try to run 3 for loops so that I'm able to create updated nums1 array. Alright, so like let's say I'll take an example. Let's say I talk about this example. Alright, so this is 3, 5, 5, 3, and then I have 7 and 7. So I'll run an iteration. I'll say for I equals to 0, I is less than n, right? And then this is I plus plus. Now inside this, I'll again run an iteration j equals to, I'll do I plus 1 so that I don't, like I want to skip I. So this becomes j less than n and this becomes j plus plus. Now inside this again, I will create, let's say, a vector, an empty vector, and inside this, using a for loop of k from n, I will push back all the elements which I feel are neither kept at index I nor j inside this vector. So let's say I'll call this as I said previously, updated of nums1. Now once I am able to do that, nums1 will be checked again. So like let's say I'll start off with a dry run. I'll say I was 0 and j was 1. That means I'll be skipping these two elements. So when I'll be doing that, I will be pushing only the elements 5 and 3 in this array. So I'll push back 5 and 3. Now, if I want initially this updated nums1 to be sorted, a small trick what I can apply is, even before starting all my operations, I can sort both arrays. Because I know after I sort both arrays initially, however I push back in my updated nums1 array, updated nums1 array will remain sorted. Yes? So initially what I can do is, I can sort these two arrays. So this after sorting becomes 3, 3, 5, 5. Now I'll do. This is I equals to 0, this is j equals to 1. That means I'll skip over these two elements. I'll push back 5 and 5 in the updated nums1 array. So I have 5, 5, I have 7, 7, differences are 2, and differences to match for every element, that means 2 is a potential answer, 2 can be pushed back. Yes, 2 can be minimized or compared with a valuable answer. Now next time j will become, like j will increase to, this becomes j equals to 2. So I'll be actually now not considering the elements, not exactly I'll be considering 3, 3, but I will not be considering 3 and 5. So now the array, pushed back array will not look like 5, 5, it will look like 3 and 5. And now in this, I know that the differences are not matching because over here the difference is 4, over here the difference is 2. So I'll not be using this as a potential answer because the differences don't match. I know I want a common x that is a difference that gets added to nums1. I don't want multiple x's. Yes, that's the case. So again, this becomes for j equals to 2, then this becomes for j equals to 3, then I comes forward, I is equal to 1, and so on. Process gets repeated again. Yes. So the dry run works and I am able to clarify the question. Now, if I look at the implementation part, is that going to be clear? Yes. How did I say I should implement? Initial logic remains same. I'll sort nums, I'll sort nums2. Nums1 sorted, nums2 sorted. Start off with an answer. Answer is initially int max. Why? Obviously because I want a very large answer to begin with so that I can minimize it later. Then I'll run a loop. I0 to nums1 size, j I plus 1 to nums1 size. Correct? This is going to run in nums1 order as n is being the nums1 size. Inside this, I have the updated nums1 array. Again, I'll run a k loop in nums1 size and I will say in this nums1, if k is I or k is j, continue because I don't want these elements. But if that is not the case, push back nums1 of k. Now once that is done, I can now start off with a flag variable, like I'll call this flag f. Flag is initially 1, which means that currently all the differences I think are same. So I'll calculate the first difference. First difference will be obviously from nums2 0 minus updated nums1 of 0. Correct? Taking one pair over here at the start. Now this difference, if is the same when starting the loop from skipping the first element, so I'll start with k equals to 1 rather, go on to the less than updated nums1 dot size k plus plus. Now if I feel that the difference nums2 k minus updated one's nums of k is not equal to difference, that means this is not my potential answer, because I know that after sorting I am having multiple x's which are getting added. I am not having the same x's which are getting added. That means I will turn my flag 0. Now if I end this for loop and after coming out of this for loop my flag is still not 0, it's still 1, that means my difference was maintained. That means all the differences, corresponding differences of bi minus ai, whatever you can call this, or nums2 of I minus updated nums of I, have equal differences. So I can say this is a potential answer. I will use this potential answer to be minimized with answer. So I can even write nums2 of 0 minus nums, or I can write simply this as difference. So I'll minimize my answer with minimum of answer comma this difference. So this helps me finally achieve the minimum possible integer x, for which removing any two possible elements I was able to make nums1 equal to nums2 by adding x to it. So the logic up till here, this piece of logic you can imagine is same as the previous case. Only at the difference is I am adding extra loops to actually take into consideration the removal of any random two elements I and j pair, such that I is not equal to j, and then I'm also having a flag variable in order to check whether I'm able to create such a difference or not. Why did I not do this previously? Because in previous question I knew that nums1 and nums2 are definitely giving me an answer, but over here I'm not sure that after removing any two elements will I receive nums1 equal to nums2 after adding a common number x. So I need to check whether the number x is common to every difference. If the differences are not common, if it's not the same difference for every element corresponding every two elements in nums2k and updated nums1 of k, then I know this is not a potential answer. Alright, now what about time complexity? So for sorting, as I said, let's say nums1 size is n, so I took this as n log n, plus this is m log m, plus now I have extra loops. So this is n, this is order of n loop, this is order of n loop, and then this is order of n loop again. So I can call this as n square. Yes, n square is definitely there, right? Or n into n is definitely there, into, now inside this I have this n loop along with this n loop again. So this is actually, you can say, like kind of like n plus n loop, right? Which is like n, which can be said as n cube plus n cube, which overall can be said as n cube only. So out of this, I know the superseding term is going to be n cube. Yes, because n log n, m log m is going to be pretty small, but n cube will definitely go in a 10 power 6 order, as we just saw over here in a brute approach. That means I can supersede other terms, I can remove, and I can report my time complexity directly as order of n cube, where n is the size of nums1. Yes, and now what about space? Am I using any extra space? Yes, I am using an extra space of updated nums1 array, in which I am pushing at max the elements of nums2 length. So I can call my space as O of m every time. Correct? Because this is compulsory for me, this is like required for me to calculate this. Now again, this can be done with a better time complexity and even by reducing the space also, but like if you don't take an updated nums1 array and you try to come up with iterations directly, that's also going to be the case, and that is definitely a potential answer. So if you have done that, that's great. But like for this particular question, for the time being, I wanted to take extra spaces and a more potential clear code, just so that for every beginner out there, we are able to clearly picturize what we are doing. So updated nums1 array is now clearly pictured. It is the number of elements I now finally have after removing the two elements kept at index I and index j. And then comparison is pretty simple, because now I don't have to like do any mathematics to iterate and compare. I can run a single iterator k and compare directly nums2 and updated nums1. So this becomes pretty easy for me, right? Again, I could have done a better optimization than this, but that is not required considering the constraints and as per the contest. Like making the fastest solution first is the bigger deal. So it's good to go, right? All right, so I think we have now ended our problem 2 also. We can move on to our problem 3. All right, so problem 3 now, this is an interesting problem, right? Overall, this is, I can name this as an interesting problem. Why? Because this uses very good concepts of bit manipulation. All right, so let us try to see those manipulations. So the problem reads that you are given two integers n and x, and you have to construct an array of positive integers nums of size n, where for every number like nums of I plus 1, it's greater than nums of I, that is like the next number is greater than previous number, and the result between like the AND operation of all the elements of nums is x. So you have to return the minimum possible value of nums of n minus 1. It's a pretty simple problem, like not simple problem, sorry, like pretty easy problem to understand. Like I am trying to create some positive integers, that's great, and they have an order of saying that it's greater, like next element is greater than nums of I. So next element being greater than its previous element. So I want an increasing order of pattern, but there's a catch that every element of nums has the bitwise AND as x. So if you take the bitwise AND of all the elements, you receive a number x. All right. Now we have to consider that we are trying to minimize the possible value of nums of n minus 1. That is, let's say you are able to create such an array in your head. You want the last value of that array to be as small as possible. So now where do we start? First of all, if we think general brute solutions, it's going to fail. Why? Because n and x both are in order of 10 power 8. So because they are in order of 10 power 8, it's obvious that I cannot just go about to actually create this array brutally. Like if I ask you, create an array of size n by this logic, and let's say you're able to come up with a good logic and you actually create this array, can you store this, or will you be able to iterate in this? No, right? Because like just to create this, you will have a very high complexity, and then the order is 10 power 8. So it's not feasible for me to actually create such an array and then report the last element. Rather, I need to come up with a solution which directly tells me this is going to be the last possible answer of the minimum value. That means I need some better approach than this. So all right, so let us first try to look at the conditions and then try to come up with an approach. So I'll talk about this condition first. This is a very important condition. They are saying that bitwise AND operation of all the elements of num is x. All right, so this is very well established. That means, let's say the number x, there's a number x, the binary representation of that number, let's say is 0, let's say is 1, maybe let's say 1, 0, 0 and 1. Let's say this is x. Then I know that I am required to create n elements. So let's say n is 4. That means I want to fill 4 elements of these 5 bits. Is that right? I'll create 4 elements. I have 5 initial empty places. Now tell me, I know that like obviously if I want these 4 elements to have a bitwise AND equal to x, that clearly means that all the bits which are set in x should be set in every number I take for these 4 elements. So let's say these 4 elements, this is A1 element, this is A2 element, this is A3 element, and this is A4 element. So since these bits are set, that means these bits should also be set in all these elements. Why? Because if I take the AND of A1, A2, A3, A4, and I want them to be x, that means if I want some bit of x which is set to also be set while I do AND, I know that I want 1 everywhere. If any one is 0, like let's say in A4 this position was 0, 1 and 1 and 1 and 0 will give me a 0 bit. And I don't want this to be 0. I want this to be a 1 bit because it's turned on in x also. Same goes for this, same goes for this. So you can actually imagine this like this, that the bits which are set are actually no longer viable for you. They are no longer, they can be no longer touched by you, or they can no longer be manipulated by you, because you need those bits to actually create your bitwise AND to be x. Now what more? Now you also want that all the other bits in x which are not set, that means bits like this, these bits are not set, these are 0. So if these bits are 0, that clearly means that these 4 elements which you now have taken, A1, A2, A3, A4, you have to make sure that there is at least 1 0 in any position of these 4 elements. So if this bit is 0, I either should say I want at least 1 0, let's say I can keep a 0 over here, then even if I keep 1 1s over here, I will receive a bitwise AND as 0. If let's say I keep a 0 over here also and 0 over here also, that's also good to go. So at least 1 0, even like a 0 over here, even like a 0 over here, that also works. It cannot be the case that you keep 1s everywhere, because if you keep 1s at all positions, then you know the bitwise AND is 1 and you want a 0. You want that this bit is 0, so you want this bit to be 0. If this bit gets turned on, you no longer have the bitwise AND of all the elements as x. So in all the, I'll repeat this idea again. So this is idea 1. Idea 1 is all bits, I can like, let me write this clearly, so that the idea is clear. All bits set in x, all right, this can be set in x, need to be set in a of I. That is all, that means every bit that is set in x also has to be set in all the AI numbers, that is A1, A2, A3, A4. Let's say, considering like, let's say I took n as 4. N can be more, like I've taken a general n. I was maybe trying to create 4 numbers. And what next? What is the idea number 2? Idea number 2 is for all bits not set in x, I want at least one unset bit in A of I. Yes, that means any bit that is not set in x, like over here this bit was not set, so you want that in any AI at least one bit is not set. So you will say that A1, A2, A3, A4 is there. This is the, let's say, column I'm talking about. So any one, like I can even take A1, A2, A3, A4, any one at least should be not set. If that is true, then I know I will have the AND value as, like AND of that bit segment as 0, and that is correct because I wanted that to become 0 since in that bit the x was also not set. So now some of the conditions are very clear. Like because of these two ideas, I have a good approach. I have a clear approach in my mind that these are the potential numbers I'm trying to create. So potential numbers will obviously have all the bits set. So up till here, A1, A2, A3, A4 will have to mandatorily look like this. The only possible control I have are over these 2 bits. And then also these 2 bits, now since I want my initial idea is to say that I want every bit, like at least one bit to be not set because these bits are not set. What I can do is, I can not set the bit in the first element itself for every bit. That is, let's say this bit is not 0, this is 0, I will set a 0 over here, I will set a 0 over here. That is indirectly saying that I will make one element as x itself. Now if I make one element as x itself, then I know for sure that now even if any bit is set in A2, A3, A4, like these all bits are blocked. I'm not talking about these bits anymore. These bits are blocked, right? These are always 1. So these are blocked. The only section I have left is the middle section where I know I have potential still bits left. These bits, this position, this position, this position, this position. So in this positions, let's say even if I keep a 1 or a 0 or a 1 or a 1 or a 1, in all possible conditions, I know that since in A1 I made sure that there is a 0 kept at that segment, always taking the bitwise AND, I will definitely get the number x. So doing this, I have now made sure that I always receive the bitwise AND as x. Is that right? Yes. Now all is left for me is to finally deduce, like in this I took n as 4, n can be a common number, n can be any random number. So all there is left for me is to deduce that after fixing these bits, which I have drawn as in the black box, this bits as 1 1 1 1 1, the leftover positions, how do I finally calculate which final number would I have received in this leftover positions? I want them in an increasing order. That means, now I'll try to bring up a rough idea. Let's say n was 4. I took n was 4 initially. So I fixed my initial number to be 1 1 0 0 1. So if you convert this to decimal, you will receive this number as this is 1 bit. Now this is 2, 4 is not set. So this is 8 and 16. So I get 16 plus 8, that is 24, and this becomes 25. So I think this number is going to be 25 if I'm not wrong. Yes, 2, 4, 8 is set, 16 is set, and 1 is set also. So now obviously I would want that whatever next number I create should be created by keeping the best possible bits first. What do I mean by that? Like initially I had 0, 0 over here. Now I have some more combinations. I can keep 0, 1, 1, 0 or 1, 1. Which combination should I use? The just next combination. I should obviously use this combination. Yes. Why? Like if I will use this combination, then I will have to use any further combination that comes beyond this. Because I know 0, 1 bit if I place, like I'll argue this. Let's say if I place 0, 1 over here, what number will I get? I'll get a number 27. If I place 1, 0 over here, the number I'll get is actually adding 4 to this. So this is 29. And if I place 1, 1 over here, I will get the number as this gets added. So this is 31. Now tell me, if I skip over keeping the combination 0, 1, then I will receive the number 29, then 31, then I'll be required to create even a bigger number than this. So don't you think my last position will start on increasing? And I want that in my array, the last number is as low as possible. So it makes sense for me that starting from the initial combination of 0, 0, keeping the free bits as 0, 0, after this, I want to create the smallest combinations first in an increasing manner. So I want to create 0, 1, then best combination, next smallest combination is 1, 0, then next smallest combination is 1, 1. So how do I do that? I can do that with a very small trick. I can say that, I'll take this to the next page. I can say that first what I'll do, initially I know that n is an order of 10 power 8. Now, keeping an order of 10 power 8, I know 10 power 8 is approximately 2 power 31 bits. Yes, I mean 2 power 31, it's actually an order of 10 power 9. But for a safe case, you can keep this as the order. So I have in 2 power 31, I have overall 10 power 9 numbers. That's the value approximately. So since I want that, what can happen is x can also have 10 power in a 10 power 8 order. It can have 1, 1, 1, 1 bit sets. So I can keep a maximum order in actually 2 power 63. That will give me 63 available bits. Yes, in the range. And in this 63 available bits, what can I now start doing? I know n is also in 10 power 8 and x is also in 10 power 8. So what can happen is x fixes out to be in 10 power 8 order, and after which I want more 10 power 8 numbers starting off with keeping a value that is minimum x, because I just established that somehow I have made a1 to be initially x. So if let's say I fix a1 to be x, the largest number I can go can be a big number that can go in order of 2 power 63 max. 2 power 63 is a good approximation, because a1 will be in order of 2 power 31, that is actually equal to x in worst case. And now if I want, after this I want 10 power 8 numbers, that means I will have to create more 10 power 8 combinations that is getting added to the initial number 2 power 31 range, that is approximately giving me a good range of 2 power 63. So I can say that I will have initially 2 power 63 bits. Alright, so I will say that initially I have 2 power 63 bits with me. So I will maybe create an array, you can say, of 2 power 63 bits. And then what I'll say that for every bit that is set in x, in this case, from the back, this is 0 bit, 1 bit, 2 bit, 3 bit, this is 3 bit, this is 4 bit, 4 bit, and then after this I have 5, 6, 7 bits, so on till 63 bits. So I will iterate in every bit, and I'll say whichever bit is set, skip on that. Because I know 0th bit is set, so I don't have the power to manipulate 0 bit again. I know that the 0 bit is obviously going to be set in every other number. So I will not consider 0 bit. I will not consider 3 bit. I will not consider 4 bit. I will be pushbacking the bits, in this, for the above, for that case, in my array, I will be pushbacking the bits 1, 2, then skipping over 3 and 4, and also skip for 0. So 5, 6, 7, 8, so on till this is going to be 63. This array is now representing that these bits were not set. These bits were not at all set in the number x. And now I have already formed one number. One number a1 has already been formed. So n is no longer 4, n is now become 3, because the elements now I want to form are 3. So I want to form 3 elements. Now look at the trick. You have n equals to 3. Represent 3 in a binary format. you will have this as 1 and 1. What does this clearly mean? Like, what does this clearly show? This clearly shows that from the back end, if any bit is set, that means you want that bit to be set also in the final number. So if I talk about the final number, this is the final number. Final number has 5 bits. In this 5 bits, this bit, and this bit is already set, right? Or you can say actually the final number does not have 5 bits. Let's say this has 63 bits. Yes, because I was talking about a big number. In the 63 bits, I know that the 0th bit, the 3rd bit, and the 4th bit are set. So this is 1, and this is 1. The positions that are left are 1st bit, 2nd bit, then 5th, 6th, 7th, so on, so on. The 63 bit, all these positions are initially left. It is up to me which bit should I fill it with. If I want to fill it with a 0 or a 1. And that decision can be made on the basis of n. I want to create at least 3 numbers. Yes. So if I want to create at least 3 numbers, that means forget about these 3 bits, like these 3 bits which were set, 4, 3 and 0. If you would only have talked about this section of bits and this section of bits, which are not filled by you currently, and I would have asked you, create a number 3, then you would have said, if the start bit from the left hand side is set, let me place a 1 over here. Now this bit is again set, let me place a 1 over here. Yes, let's say n was 2. So if n was 2, then this number would have actually been equal to, let's say, the number 1 and 0. Yes, let's say n was 2 in this case. So for 1 and 0, again you would have argued from this that from the left hand side, this bit is set. No, this is not set. So I'll not set this bit. This bit will remain 0. Now, is this bit set? Yes, this bit is set. This is 1. So let me set this bit, and this bit is going to be set. And then all the rest bits are not set. So this again remains 0. Everything remains is 0 over here. So this number 1, 1, 1, 0, 1, if you look at this number carefully, isn't this number A3? And wouldn't you have received the best optimal number A3 as your final number if initially your n was 3, right? If initially n was 3, that only means n would have become 2, correct? So if initially your n was 3, that means n became 2. That means you actually set out for 2 best combination numbers in such a manner such that the final number turned out to be the least possible combination. Yes, so this is what my whole idea is going to be looking like. Now, if I actually implement this out on the test cases, I think things are going to look much simpler. So I'll talk about both cases so that things become clear. N is 3, x is 4. Let's picture out x4. x4 means 1, 0, 0. So I want 3 numbers, a1, a2, a3. I know that this bit is always going to be set. So I'll fix this, 1, 1, 1. And now I'm not going to hamper this section. The bits I have to choose are these empty bits, along with having extras like bits in over here, like in a1, a2, a3. I have more bits, like I have taken a 63 order. So I have 0, 0, like I have like empty bits over here also, like here also, right? Up till 63 limit. Yes, only this bit is set. Now what I'll say, like over here also I have 0, 0, zeros over here. So this bit is set. Now I'll say, in my vector of unset bits, I would have pushed the position 0, 1, 3, 4, 5, so on till 63. Yes, these are the bits that would have been unset as positions till 63 bits. Now I would have decreased n first by 1. So now n becomes 2. Why n2? Because I know first number has already been declared. First number actually looks like something 0, 0, 0, 0, 0, 0. This is 1 and then this is 0, 0. Why have I made this first number fixed to be? This number is actually 4, you can say. Because I know that fixing this number is going to make sure that my bitwise AND turns out to be equal to x. Because this number is actually x. So if I AND this out, all the bits are 0. This is 0. Only the bit that is set in this number is actually set in x. So ANDing this number with all the other possible numbers is always going to result me the bitwise AND as x. So that condition is checked. Now I have this segment left over to operate on. I can say that the better ideal condition, now n is 2. So in binary format, this is actually 1 and 0. From the left hand side, this is bit 0. So I know this should not be set. So in the final number, I have a final number with me. In the final number, I have the initial final number that looks currently like empty, 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 empty. Then I have a 1. This is at the bit position 2. Then empty, empty. Now I have from the left hand side 0 bit. So I'll not set this. This is 0. Now I have the 1 bit set. If this is 1 bit set, then I will say that in this position of 1, I am going to make this also as 1. This will give me a number that looks like 1, 1, 0. And this number is actually equal to 6. And 6 is a good case because 6 is the lowest final number you could have created, which would have given you a total length array of 3. So start number is 4, next number is 6, and you can very clearly picture that if next number is 6, the middle number should be 5, because the combination which I left out, which was actually lower than 6, was actually a combination that looked like 0 and 1. Yes, so this is how the case is helping me. Now if I extend this to case number 2, again, n was given 2 over there, x was given 7 over there. Let's represent x in binary format. This is 1, 1, 1. So I know in my final number, I have some bits as like empty, then last 3 bits are set. So in my vector of unset bits, position starts from 3, 4, 5, so on till the number 63. So these are the positions. This is 0, 1, 2, 3, 4 up till indexing. Now in the number n is now reduced to 1 because I only want to create one number. 1 in binary format is actually 0, 0, 0 something. You can call this as finally 1. Like this is total 60, if 63 bit representation is there. From the left hand side, I have the first bit as set. That means the first bit over here from the 0th index will also be set. So I'll set this as third bit also. So this is 0 bit set, 1 bit set, 2 bit set, and 3 bit will come from being set in the, like initially it was unset in the vector. It gave me the position that this is unset. So this becomes set now. Yes. And this is how I have created a new number, that is 15, and 15 matches. 15 is the final answer. So I think the approach is pretty clear. Now this can become pretty confusing, right? You can actually implement this out on your own and look out for some more test cases, and you will understand that what idea am I trying to come up with. Alright, so I think this is pretty clear. Like the x idea is also pretty clear, that we were trying to find bitwise and to be equal to x. So I made sure that when I made a1 equal to the number actually equal to x, that actually created such a structure that now if I AND it with any value, a1 will always make sure that I have the number x with me. Making sure also that the fact other numbers have those bits set also in which x was set. So as I showed that, let's say these 2 bits are set, this bit is set, then all numbers have those fixed bits. I am not going to hamper those bits again. The control I have are only over the control bits which are not set. So this is what I've done in the code piece also. I have the answer with me, that is x, that starts with 0. I have a vector v, that is the unset bits. Now I have run a loop from 0 to less than 64, that means up till 63. And then I'll say, is this bit not set? If this bit is not set, that means it will give me a value that is 0. Turning on that bit will become 1. So I'll say x and with left shift 1 to I times. Now I have 1 LL because I am considering in 10 2 raised to 63 power order. So you can also take this as 1 LL, right? If you don't take this, this is going to be a common mistake. You will get an integer overflow. So take this as 1 LL. Shifting 1 LL to the left to I times means multiplying 1 considering the value of 2 raised to I. This is what is the physical meaning of 1 LL left shifted to I. Now if I do this, that means I'm trying to basically create numbers in which only one bit is set. So like 1 0 0, this is 4, or let's say powers of 2 basically. So this is 1 1 0 0, this is 8, this is 4, so on. So now I'll say if that particular bit, I'm trying to extract that one bit, if that one bit corresponding when ANDed with x for that bit gives me a bit that is not set, and taking the not of that will be 1, that means this is set. So I'll push back that index in v. And then I will decrement n by 1. Then I'll do the same thing, start with 0 to 64. And then I'll do the same thing with n. So as I did with n, I will run the iteration from the backend side because I'm starting with 0 bits. If this is set, that would mean n and 1 left shift to I again gives me a value that is greater than 0. This means this is greater than 0. And if gives me greater than 0, that means this bit is set. If this bit is set, then I want the corresponding I value, I index value in the bits, like from that extracted bit of the unset bits in the array v, to also now be added to the answer or get set in that answer. So that means simply adding on to the answer this vi bit, bi bit was 3, so 1 left shift 3 to this answer gives me the corresponding answer up till here. Now up till here the answer is only the answer that has never considered that you are starting with the number a1 which is already x. So for that what will happen is you need to increment answer by x again. Because like up till here, what your code will give you, code will only give you the number that looks like this. 1 1 1 0 0 0 0, because in this bit is set, so you will fix the 3-bit, but other numbers are initially 0. But you don't want this. You want that you started off with x as the initial part. So up till here you have only found the range, and you want to shift that range by x. So you can increment your answer by x again, so that these bits are turned on again. So x is actually 7, so these bits get copied, pasted in over here, and you set them again in the bit over here. You can actually even avoid this by even starting your answer with x. That is also going to give you a correct answer. And if I submit this out, I think you will see I get an accepted solution. Yeah, voila. All right, so now if I discuss the time complexity, right? For time complexity, you are obviously making 64 calls in the loop. That means O of 64 is a good order to talk about the time complexity. And what about space? I'm using an extra bit, extra vector to save the unset bits. Maximum order of that array will also be 64. So I can say now time is also 64, which is almost constant, like this is almost constant, right? And space is also almost constant, which is good to go, because I know for an order of 10 power 8, I was required to create a solution that runs in a almost constant or a root n complexity. Like I could have not gone in an O of n order complexity. Yes, so this is why now the question is fully solved, and the question definitely submits out. Okay? We can easily see that yes, we got a right submission in this. All right, so now we can actually move on to the fourth and final problem and understand its idea. Like according to me, my description, fourth problem is actually much easier to understand as the third problem, because third problem has very intricate bit manipulation. All right, so let us talk about the fourth problem. All right, so I'll clear up the pages. I think I have enough pages to go, right? Let me create some new pages, and then we will discuss the fourth problem. All right, good to go. Yes. So now find the median of the uniqueness array. Now what does this mean? You are given an integer array nums, and the uniqueness array of nums is the sorted array that contains the number of distinct integers of all the subarrays of nums. In other words, it is a sorted array consisting of distinct nums of I to j for all 0 less than equal to I, less than equal to j, less than equal to nums of length. Now here distinct of nums of I of j denotes the number of distinct elements in the subarray that starts at index I and ends at index j. So like the story is very complicated. The main part actually starts from the sentence number 2. You have been given an array nums, and you are trying to create all possible subarrays of that nums array. And in all those possible subarrays, like for any one subarray if you consider, the number of distinct elements in that subarray is actually the number which you want to denote. So they will say that you will return the median of the uniqueness array of nums. So let us look at the test cases and we'll understand what is happening. Let's say the array was, like I'll talk about the second case. Let's say the array was 3, 4, 3, 4, 5. In this case, uniqueness of this subarray is 1. Uniqueness of this subarray is 1. This subarray is 1. This subarray is 1. This subarray is 1. Now uniqueness of this subarray, 3, 4 is 2. This is 2. This is 2 and this is 2. Uniqueness of this subarray is 2. Uniqueness of this subarray is 2. Uniqueness of this subarray is 3, because I have 3 distinct elements. Uniqueness of this subarray is 2. Uniqueness of this subarray is 3. I have 3, 4, 5. And uniqueness of this subarray is obviously 3. So if you look at the case, I have 1, 1, 1, 1, 1. 5 times I have had uniqueness 1. Now I had 2, 2, 2, 2, 2, 2, 2. 7 times I had the uniqueness as 2. And then 3, 3, 3. 3 times I had the uniqueness 3. After sorting this uniqueness array, like after finding all the possible distinct uniquenesses, when I kept them in an array, sorted them, the median of that array turned out to be 2. That is why the output was 2. So now what is the problem boiled down to be? The problem has boiled down for you to somehow calculate the median in such a uniqueness array, or such an array rather, in which every element represents some sub-array's distinct element count. Is that right? I'll boil this question down again. Your target is to find the median of the array created from the elements, yes, where I'll say each element is actually the count of distinct nums of I in a range or a subsegment you can say, or a subarray in a subarray from I to j. Alright, and again you can call this nums of k rather, where k is actually extending from I to j range. So your target has now become that you somehow you are able to calculate all the subarrays. For every subarray you are able to also calculate the number of distinct numbers that come in that subarray, push back all such distinct numbers in a new array, and that array, uniqueness array, is what they are calling it, find its median. So now if I start thinking brute approaches, now once the problem is clear, if I've understood the problem, if I look at the constraints now, constraints are very huge, right? 10 power 5. So if I ask you, can you actually create every subarray? You will say no. Because to create every subarray, I will require 2 loops, and that will give me an n square complexity. Even if I create subarrays to find the uniqueness, I will require again some other map or some data structure which could have given me the final uniqueness, final distinctness in that particular subarray. So that's also going to be an added time complexity. And even before this, subarray calculation is not possible. That means the approach of calculating subarray is not at all possible. You cannot calculate every subarray. You need a better approach than this. Yes? So now what better approach can come to my mind? Now when I was reading this problem, when I looked at the test cases, I noticed one thing. The thing I noticed was this uniqueness array is sorted. Yes, they have said that uniqueness array is a sorted array. And in this sorted array, you are trying to find which is a median. So I can argue that the median is 3. I can argue that the median is 1. I can argue that the median is 2. Let's say I ask you, in this sorted array, you want to calculate the median. So first I'll ask you, in this sorted array, the sorted uniqueness array, what do you think is the largest term and the lowest term? So if I ask you what is the lowest term in this array, you will say 1. Yes, because I know uniqueness, minimum uniqueness is going to be 1. I can take a single array, single number, and its uniqueness is 1 as a single subarray. And what is the high point of this uniqueness array? This uniqueness array high point is actually the total distinct count in whole array, Yes, in whole array. Now if I ask you, the median only is going to range between this low and high. Yes, median is definitely within this high range and is definitely greater than this low range. Why? Because this median falls somewhere between these two. Either it's the lowest one or it's the highest, that is the whole uniqueness, that's the whole distinctness, of the whole array. It somehow falls in between, or it's equal to low, equal to high, or it's somewhere in the between. This is the range of median. And again, looking at the uniqueness array, this is sorted. So can I think to binary search? Can I think of binary searching on the median or for the median, considering low and high as declared above? Can I do this? Let's say I have declared low as 1. High I know will, somehow I can calculate high very easily. I can maybe create a map and I'll directly get the distinct count in the whole array. Not a big deal. Now, for this example only, low will be 1, high will be 3. So if I want, if I say I can binary search on this, what does it mean? I can say that what I'll do, I want to minimize this, I want to create I want to return the median of this uniqueness array. So that means let's say I calculate the mid of this. After I calculate the mid of this, mid comes out to be equal to 2. Yes. So for a median, I'll increment this idea. For a given array, A1, A2, A3, A4, A5, and let's say that's all. I have total 5 elements in this. Now, if this array is sorted, I know the median is A3. Looking at this array, I know this median is A3. That's true. But one more fact is related to this? One more fact that is related to this is, if A3 has to be the median of the whole array of size 5, that means there has to be at least, I'll repeat this, at least 5 plus 1 by 2 or better you can call this as 5 by 2 sealed elements less than equal to A3. Yes, is that the required condition? If I want A3 to be the median of this array, A1, A2, A3, A4, A5, then don't you think I want that, if I'm arguing that A3 is the median, that means elements less than equal to A3, the count is actually at least equal to the 5 by 2 seal value, or the total size by seal value. That is actually, in this case, like if you do 5 by 2, that is 2, seal 2.5, if you seal this out, that is 3. So tell me, how many elements do you think are less than equal to A3? 1, 2 and 3. So that, by that case, I know A3 is a median. Now if I argue the same for A4, do you think A4 can be a potential median? You can say yes, it can be a potential median, because number of elements less than equal to A4 are actually greater than equal to 3. Number of elements less than equal to A4 are 1, 2, 3, 4. 4 is greater than equal to 3, so I know A4 is a potential answer. So now can I start thinking in a binary search format, because I know I am able to see sort of a monotonic predicate case. How is that possible? How is that possible? If let's say I have the initial, like the lowest median I can go is 1, and the highest median I can go is, let's say, this unique number. Let's say I'll call this number, like I have a unique number, let's say maybe I'll call this number u. So let's say now I calculate a mid is actually 1 plus u by 2. So after I calculate a mid, I will ask you, for this mid, tell me, do you think if this mid is a potential median of the uniqueness array? So I will say that for this mid, if I want to answer yes or no to the query whether I feel this median, this mid is a possible median, I will say that it would mean at least, let's say the size of the uniqueness array is n, at least n by 2 seal elements in the uniqueness array, in the uniqueness array are less than equal to mid. Will I say this? If I find this condition to be true, then don't you think this mid value is true? So now if I ask you the predicate logic, there are values from 1 to u. So this is 1, 2, 3, 4, 5, 6, so on till this is u minus 2, u minus 1. So if you find a mid, and for that mid, the answer for this query, like this black box query, if for this black box query, that you are somehow able to create a black box, and that black box is able to tell you that the count of sub arrays having the distinct count is less than equal to mid, and this count is at least the seal of n by 2, that is the total size of the uniqueness array. If that turns to be true, then don't you think I will have true for all the rest numbers above also? Yes, if I have true for this mid, if like this is the mid, like if let's say this portion is the mid, if the here it is true, then above is also true. Yes, because if I'm able to find at least elements at this particular area, like for this particular number, then all the larger numbers I will definitely be able to find. And somewhere or the other, if I'm not able to find false, like if I'm able to find a false, if I get a false, that means everything below that is also false. And my target is now becoming to actually find that one position where I have found a true. Because previously, before that, everything is a false. After that, everything is a true. My target is becoming to find somehow that one true where I will say this is exactly the median I was talking about of my uniqueness array. So if I am able to understand this, all that is left for me is to somehow calculate this predicate logic, somehow calculate this checker function which actually gives me the answer. So up till here everything is clear. I have understood that I will want to run a binary search on the uniqueness array. Yes, on the uniqueness array from the range of low 1 to high as total unique number in the whole array, whole initial array. When I will find a mid, I will pass that mid to a checker function. That checker function will return me true or false. It will return to me true if it feels that there are at least n by 2 seal count of sub arrays in the original array for which their distinct count value is less than equal to mid. Yes, at least, I will repeat this again. It will return a true if I find at least ceil of n by 2 elements, like, ceil of n by 2, at least ceil of n by 2 count of sub-arrays whose distinct element count is actually, you can call this as, like, I'll rub this off again, distinct element count is actually less than equal to mid. If I'm able to get this number and if I find it true, I will say bring my high to mid minus 1. Store this as a potential answer and bring my high to mid minus 1. And if that is not the case, if I find a false, then I will bring my low to mid plus 1. Alright, so now how do I finally calculate the checker function? Now this becomes the second part of the question. Up till here everything is clear. Yes, target has to become binary search. Why binary search? Because that is going to fully remove the concept of not finding the possible answers like in a very long time complexity, in a very harsh time complexity. This is definitely going to increase my time complexity by a greater margin. And now if I'm able to calculate the checker function, I will be good to go. Now how do I calculate the checker function? I'll say that checker function is trying to calculate the sub-arrays whose distinct element count is less than equal to mid. So this becomes a sliding window sort of a technique. Yes, what can I do is, I have the elements, I have A1, A2, A3, let's say I have A4 and I have A5. I can start off with a window kept at L equals to 0, R equals to 0. That is meaning window over here. In this window with, let's say, an unordered map, I can increment the frequency with this map of A1. Now I'll say till I feel that in this current window, the map size is actually, like, if I feel that this map size is actually greater than equal to mid, that means the distinct count is greater than equal to mid. If I feel it is less than equal to mid, I will keep on incrementing R. That is, I will keep on incrementing R. I will make R shift left. I will make R1. Even if I am still good to go, shift again, R equals to 2. Still good to go, shift again, R equals to 3. But as soon as I feel that I am not good to go anymore, I will start decreasing my range. That means up till here, let's say I covered up till here this range. If I feel now my map size has gone greater than mid, I will start bringing my range forward. So I'll start bringing my 2-pointer approach, like 2-pointer as like L, forward to decrementing A1, removing this A1 from the window accordingly, and only considering the window of A2, A3, A4. If it's still not good to go, even shorten this window again, like bring L more forward. L now comes over here, and this is the new window. And every time I am standing at a window, every time I feel that I'm standing at a window, let's say I'm standing at this window, I am going to increment the size of this window in my net answer. Why? Because that size of the window will actually dictate that up till here, if I would have considered, like if I'm talking about this window, A1, A2, A3, A4, till A4, the window that is there, I will say that the total size is 4. So I will add 4 to my answer, which would mean that if in this window, the map size is less than equal to mid, that means any subarray in this window which ends on A4, that is this subarray, this subarray, this subarray, and this subarray, all will have a distinct element count less than equal to mid. Because I know the whole array from A1 to A4 has less than equal to mid distinct count, then all the subarrays ending on A4 will also have that. So every time I increment my R windows range to forward, I will keep on adding the answer as I please. And that is where I can start incrementing my final approach. Alright, this sliding approach is like, it's a very common approach to understand. Like if I'll show you the code, you will identify it very quickly. The actual question, like this is actually a separate question on Leetcode or some other platform itself, where if you actually search this question separately, question being, find the number of distinct elements in subarray, like find the total count of subarrays having distinct elements less than equal to some number X. Then this becomes a separate question. And this is actually solved by an approach called 2-pointer plus sliding window technique. Alright, so I'm not going to go in detail of the sliding window technique, right? This is a very common technique you must know, right? What I'll do is I'll run this on a very like sample case. I'll run this on one sample case so that things become clear what we are doing from the binary search to the end position, and then we'll dive into the code. So I'll take up the example 3. This is 4, 3, 5 and 4. Now first I'll calculate low. Low is 1. Minimum median can be 1. What is the highest median? Highest median can obviously be the total distinct count in this whole array. So this is 3. So highest median is 3. Now I also want one thing. Over here I took n all the time. And what was n? N was the size of the uniqueness array. So how do I calculate the size of this uniqueness array? Like this array. This array has the size 1. This array total has a size of 9. So how do I know that the size of this array is actually 9? Like this is 3, this is 3. Not 9, sorry. This is 10, sorry. My bad. How do I know this size is 10? Because this size is coming from taking into consideration the distinct values that would have contributed from all the subarrays of the initial array. Now, now the question is to calculate how many subarrays are there for an n-sized array. Answer to that is actually n into n plus 1 by 2. So if n is 4 in this case, like the start size of the array is 4 in this case, then I know that 4 into 5 by 2 gives me 10. Which actually means that the size of the uniqueness array, if I call that size as m now, right? If let me call that size of unique SU, let me call that size of uniqueness array, that is actually equal to 10. So now I have 10 also available with me. Why did I require 10? Because I want to check at least this, I want this black box to be checked with this at least variable, yes. So for this, I wanted this n value, right? Or now I have replaced this as SU value, yes. N is the size of the array, so SU is the size of the unique subarray. So if I want this, now I can run my binary search. So I run my binary search, I say mid becomes 2. For a mid equals to 2, I will run a checker function. In this checker function, I start with this. I have 4, 3, 5 and 4. Begin with L equals to 0, R equals to 0. And initially I have a map, everything is empty. Inside this map, I increment the frequency, I insert 4. So I'll say 4's frequency became 1. Now currently my map's frequency, mid is 2. So map's frequency 1 is less than equal to 2. So I'll not do anything, I will increment my R. R is shifted to 1. Now map has 4 equals to 4, 1 and 3, 1 because it has 2 elements. Now this map size has become equal to 2 and 2 is still less than equal to 2. So not do anything, increment and go on. This becomes R equals to 2. Now when I do this, I know map size has become equal to 3. 3 is greater than 2. So up till 3 is greater than 2, what will I do is, up till 3 is greater than 2, I will decrement L. I will say that don't I will increment L and remove from this window size, up till here I was having this window, now I'll start off chopping of the start windows. So I'll say bring L to forward, remove L from here. So now in the map, I no longer have 4, I only have 3 to 1 and 5 to 1. And now my window is looking like this. And I keep on doing this every time. And when I do this, my thing is to calculate the count. How do I do that? From the start, if I was having R equals to 0, R was initially 0. So when I had inserted 4, 1 to this, then I would have added the value count as 1 because R minus L plus 1 is actually, currently this is 1. So count is actually now 1, which shows that there is a single subarray 4, which would have given me the count of distinct as less than equal to 2. Now when I would have incremented my window to R equals to 1. And again, when I would have said that my distinct count is less than equal to 2, I would have said add R minus L plus 1, that is 2 to this initial count. So this becomes 1 plus 2, this is 3, which clearly shows that now I have 3 distinct subarrays, which have a distinct element count less than equal to 2. One is this, and one is this. So this happens every time, and now I have a final approach. Alright, so if you dry run this out yourself on pen and paper, you will clearly understand the idea. It's not a very tough problem from here. And somebody who has read sliding window plus 2 pointer technique and somebody who has quickly figured out that this is a binary search question will be able to actually implement this question before the third question itself. And this is actually what happened with me also. I was able to implement the fourth question well before the third question, because the fourth question is something that is based on concepts which we have already covered, which people have already covered. Sliding window and all these techniques are very common techniques which most people have covered. So now if I look at the code piece, how do you think it's going to be? L is 1, R is m dot size. How is m coming? M is the map. So I have used an unordered map to calculate the total distinct count in the whole array. So R becomes m dot size. I have an answer. Now I have the n is the num size. I will calculate the total subarray count. Total subarray count is n into n plus 1 by 2. That is finally like for over here, I saw that I wanted 10. And then the checker that is minimum median, that checker which I am going to compare it with is actually, this is actually going to be total sub plus 1 by 2, or that meaning total sub by 2 seal, or you can do total sub plus 1 by 2. Now what will I say? Like in this, when I calculated the total, like when I would have calculated the total subarrays, I would have actually gotten, like in this case, I would have gotten the total subarrays as, like I would have gotten a net count of 7. And since I knew that 7 was greater than equal to, like 7 was actually greater than equal to 10 by 2, this is actually 5. That means this mid would have been a potential answer, and I would have shifted my high from 3 to 1. Yes, and low would also have been 1. And answer would have been saved as 2. And then I would have done a binary search on 1, 1, and then I would have not gotten an answer over here, because I know that that would have not been the case, and 2 would have been reported as an answer. So I want this value. That means I again need to divide it by 2. So I'll calculate total sub plus 1 by 2, so that I have a seal value. Yes, the seal value. Why seal value? Because like as I showed over here, seal value. And again, like seal value can also be like thought in your mind by this statement. I like missed this statement. Median is defined as the middle, and in this they have very clearly said that if you have two choices for median, you want the smaller value. So if you want the smaller value, it makes sense for you that in an even array it would be simply by 2, and in an odd array it would be the seal value. So if you take seal value directly, it is still going to give you a good answer, because like for seal of 6 by 2, like if you calculate, if you have a total size of 6, then 6 plus 1 by 2 also gives you 3. And if you want to calculate for like odd size array 5, then 5 plus 1 by 2 also gives you 3. So either way, like 5 plus 1, that is 6, also gives you 5 plus 1, that is also 6, by 2 also gives you 3. So in any case, you are good to go. So that is why if you take directly seal, it's good to go. And I have written that seal technique by simply saying total sub plus 1 by 2. Now the binary search. L is less than equal to R, mid calculation L plus R, left shift equal to 1, or simply you can say this is by 2. Both things are right. Pass this mid to the checker function with the nums array, nums.size, and then check whether the count which I finally return from this check function is greater than equal to the median mid. If that is the case, it's a potential answer. Turn R to mid minus 1. And if that is not the case, turn L to mid plus 1, opposite thing, and then return the answer. Good to go. Now if I look at the binary search, sorry, the checker function, nums array and mid. How do I calculate? Have the count is 0, unordered map, m, L pointer, R pointer. While R is less than equal to n, first increment that window in m. While I think that m's size is greater than mid, decrement the start window. If it's all it has become equal to 0 frequency, then erase it directly and increment L plus plus. So this is the while loop that will help me stay in the window of having distinct element counts less than equal to mid, and then increment my count as R minus L plus 1 and increment R plus plus. So this runs a 2-pointer window technique and finally returns my count. Now if I actually submit this out, you will be seeing that this gets you a right solution, which is obviously like that's obviously going to be the correct case because this is the correct solution. Now if I calculate the time complexity, right? Initially I have the time, I will have some time to actually create this frequency map. So for that you can say that unordered map runs in O of 1 complexity. So this is a simple loop on the array n. So this is n size, n iteration, this for loop. Now the binary search. Binary search limit is actually dependent on like you have a log of search space. So you can say log of search space. Now search space is actually from 1 to, what is the search space? Search space can be actually equal to the distinct element counts. Now distinct element counts can obviously not be greater than the n size. Yes. So I can say log n is the search space. Into you have the check function. Check function is also a 2-pointer approach. It's again using an unordered map. So incrementing and decrementing and erasing everything is O of 1. But in this 2-pointer approach has a sliding technique that actually runs in 2 into n order. Why 2 into n? Because you have 2 pointers. So it can happen that both pointers need to traverse the whole array once. So you write this as 2 into n. So you can say that log n into 2 into n is a good approach for the checker function. But again, because 2 is a constant, so you can actually remove this and write this as log n into n, which is actually simply as n log n. So overall time complexity is actually n log n. Width is definitely within my boundaries. In this, the superseding term is actually n log n, so you can remove this and write this as n log n. And for an order of 10 power 5, n log n definitely works. Now what about space? You have O of some space over here. Space can be written as, like you are taking the unordered map everywhere, like over here also, you can take space as n. Yes, and both these time and space are good to go. They are well within my boundaries. So if I submit this out, like we have an accepted solution and it works. So what is the takeaway from the problem? Takeaway from the problem is to understand that, like, the exceptional case in this was I observed that the median uniqueness array was sorted. Even if I did not observe this, this was clearly written. So if you're able to read the problem and understand that something has been sorted and you're actually trying to calculate your answer on a sorted structure, binary search is a possible case. And then all that there was left to do was to somehow figure out a checker function for this. Once you were able to do that, this question is again few lines of code. Right. So I think this is where we can stop. This is a good place to stop, and this is what brings us to end of all our 4 problems. All right. So thank you for watching the video. I hope you like it.